Alright, so we're going on to question 16. As you can see, this figure shows the relationship between the number of miles per gallon on the highway and that in city. Just a comparison here. You're going to get more highway, right? So like we can see in observation, you're going to get more highway than you get city. You're constantly moving the throttle around, so that's going to force more gas into the system. I imagine I'm more of a carburetor guy, but I imagine that's the same with the fuel injected system in the modern cars. I was a muscle car guy, so back in the day. And notice they give us the equation right here, and notice they put in the independent variable city mileage and the predicted highway. So the independent variable is city, dependent variable highway. Predictor variable or explanatory variable, response variable, or we could call it the predicted. So select the choice below and fill in the answer boxes to complete your choice. For an additional city mileage, so we're talking about the X here, the highway would go up by this value right here. So this one was a little confusing earlier. So I don't think we want to talk about more than the city. Of course, we get highway mileage is the times the city. That's not true because we got to factor in the y-intercept for each additional city mileage. The highway value goes up by that many. So this many, that makes sense here because we're really thinking about 9, 4, 7, 8. It goes up by that much times the city mileage. Let's see. There we go. Yeah, just think of that as like what's being multiplied by the city mileage. That's one way to interpret that. A lot of these others are getting weird, but they're definitely distractors, and they throw in the additional chaos. Or you're answering one thing, or you're filling in two blanks. But you got to read it very carefully. So I'm going to select on this one, select the correct choice below. A car's predicted highway mileage is. A car's predicted highway mileage is. Highway mileage goes up by. Well, that one's true, but I'm not sure if that's what we're asking. If the car were to get, it would get. I mean, it is. It doesn't ask. Oh, you gotta look up here. That's the key. We're talking about the intercept. This would have been. This is very tempting to answer the same thing you had in A. But if you look up here, part B is supposed to be all about the intercept. So we're going into one of these, the intercept, because no cars get in the city. Man, this one, the wording, a car, so like there seems more than its city mile. If the car were to get 0 miles per hour in the city, yes, that's what we're looking for. 0 miles per hour in the city, it would get the intercept 7.0 7.92 on the highway. That should be it. Oh, what happened here? Yeah, I don't know. This one was weird, right? So that's a good thing I went through this one again. Select the choices. So this is part B. Either interpret the intercept or explain why it is not appropriate. So this is the not appropriate to get. No cars get. Yeah, I think that's it. 0, and then we're talking about the X value. So you got to think of this way. That's the intercept is 0. That's when X is 0. That's got to be the one. That's it. That's it. So be careful with that one. And I misinterpreted that one twice so far. So that's possible problem area, or I just don't know what I'm talking about. The thing is these different things, and anyway, you get the idea. So let's go on to the next one. Alright, so here we go. We're going to code this, and I'm going to code it without any. I'm going to code it completely on the screen. Completely on the screen. This is similar to sampling by using a random sample. See, we're in chapter 5 and we're getting into these random sample. Notice we're talking about a randomized experiment because it is an experiment, because we are separating them into 2 groups. Notice we have 20 college students, so we should have 20 blocks here. And we want to have each getting an equal chance of being assigned to either the computer group or the pen group. That's the fairness of a randomized experiment. Everyone has the equal chance of being assigned to either group. So what they want to do is let the even digits be the computer group and the odd digits be the pen and paper, or whatever they're talking about here. But first, this one is just going to ask, it's not asking for that assignment yet. That's what I started thinking. Let me go ahead and do the assignment. But it's not asking for that just yet. So what we're going to do here, going back to what we were talking about way before, and that is a seed, and the seed is right here. Begin with the first digit in the 3rd row of the accompanying random table. So we're going to begin with this first digit in the 3rd row of the accompanying table. That's our seed. So the first digit is a 1. And you can kind of do this. You can go to tabs here. 1, and then we got a 7. Then we got a tree. And remember, I'm on the 3rd row here. I just did the first bit. Now I'm going to start the second bit. 1, 4, 8, 5, 4. I just did the second bit. Now let's do the 3rd bit. 6, 5. Oops. See there, I didn't hit the tab. Hit the tab and it'll go over there. 6, 5, 5. Tree, 0. And then we're going over to the 4th bit. 2, 2, 4. Tab it. 2, 2, 4. A 6 and a 6. That makes sense. We got 4 bits. There's 4 in each bit. 4 times. Well, there's 5 in each bit. 4 times 5 is 20. So we'll go ahead and check. Let's just check our answer here. There, we got it. Now we're going to convert these over. Now we don't need that table anymore. We don't need StatCrunch anymore. Let me save some RAM on this old computer here. Now all we got to do is take these odd or evens Remember, computer is even, or C, and P is paper. So we got an odd, so that's paper. 7 is odd also, so that's paper. Tree is odd also, that's paper. Niner is odd, so that's paper. Niner again is odd. 1 is odd, and then here we finally have a computer group with the 4, an even number. Then we got another even. Then we go to odd with the 5. Then we got another even with the 4, even with the 6, odd with the 5, odd with the 5, odd with the tree. 0 is even, because it'll divide by 2, so 0 is even. 2 is even, so it gets a computer. 2 is even, so it gets a computer. 4 is even, it gets a computer. 6 is even, it gets a computer. And 6 even, we get a computer. Let's check it. There we go. Notice it started off pretty chaotic with all papers, but it kind of evened out. So now we just got to count up. So let me show you something here, how to do this using the complement rule. That way you don't have to count up both the C's and the P's. Let's just count the P's. There's 1, 2, 3, 4 P's, 5 P's, 6 P's, 7 P's, 8 P's, 9 P's. We got a 10 P. So if there were how many? 20. And I think I just counted all the P's. That means, right, let's bring up Desmos. If our P, and then don't get this confused with the proportion, if our P is 10 and our N is 20, our computer should be N minus the P, right, or the P. So we should have 10 and 10 here. If I didn't do anything incorrect by counting, I'm just going to count again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and there's no more P's. So that should be our breakdown here. 10 to 10. So what percentage were in the computer group? So you say 10 out of 20, but notice this key. Simplify your answer. And that's a pretty easy one to do. But remember, StatCrunch will do something if you end up with something a little more less old school, simplifiable. Remember, you can hit that button right there and it'll turn it into a reduced fraction for you. So they want 1 over the deuce. And I think I put a half in there. I don't see anything indicating if I should put it in as a decimal. So I guess we just assume that it wants the fraction. Oh. So it's saying I miscounted here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, there we go. 1/2 converts to a percentage here, right? See, it's all misreading. So it's actually 50%. Can't even remember what the delete key is at this point. We get rid of the whole thing here. And there we go. We can put our 50 in. There we go. And then now D. So this gets a little weird here. And notice it's saying describe another way. Another way we could do the random number assignments. And that's not the only way we could do it. With odds going to paper and pencil and evens going to computer, we could assign the first 4 or 5 digits to computer, or pen and paper, and those to the computer group. That makes sense. So we would check it, and I think, does it say, oh yeah, keyword here, select all that apply. So there's more than one answer. So here, assigning those to the computer, those to the pen, that's possible as well. What gets different is when they throw in the 10, our table only was dealing with one-digit numbers, so C is definitely not an answer. So, or we could have done it the other way. Remember, we had the evens going to the computer group. We could have done that. Notice this one has the 10 in it. So see, oh. And that should be my answer. Yeah, there we go. Alright, so that's 18. Let me save my stuff so my computer doesn't crash. So this one is a pretty good one about probability. 5 to 11. But let me, so like I'm not a card player, so when I see this doesn't, like just drawing an ace, it doesn't correspond in my brain as quickly, and that may be the case with you as well. The cards I usually play are your Crazy Eights, your Uno, I don't know, those games. Those are the cards, because I don't like to think too much during my time off. But anyway, if you go over here into the week 5, maybe I put it into the final exam. Okay. See, that's one of the things here. Maybe I put it under this random modeling. Yeah, there it is. So, probably to make more sense of it, and y'all can't see it, evidently. Let me make sure it's visible. I don't know if I can copy it and put it somewhere. Well, right now it's in week 4. Let me try to put it also in our final exam stuff here. So, what do we got? Practice, final exam, some final thoughts. So, spend a little bit of time here showing you where to look for this, because this is kind of an important problem. It's got some big points going, or it's got some multiple parts to it. So, I'm going to create a new one here. Wait. I should be able to go over here, and since I've already got it created, add an existing, and I should be able to, nope, it's still, if I can get the content, no I can't, they changed things. So anyway, what I'll do is make a new one here. I'll have to make a new one in there to put it into the final exam so you can have easy access to it. But right now it's in the random modeling. I gotta get the image back in there to get it for you. But anyway, there it is right now. You can see it in the week 4. I saw, or oh yeah, it is in the chapter 5. Oh, it's in the week 4. So it's in week 4. Sorry guys. Anyway, you see what we've got to use here. I'm going to go ahead and bring up that page, and I'm going to use that as I work through this. Make it a separate page, so maybe I can hold it, put it there, and then do the homework over on the side maybe. So we have this layout, and it describes it for the layout of a deck of cards. So drawing an ace. Notice that we should have 4 aces here. There's no other aces. So what we're talking about is a 4 over the total number of cards in a deck, which is 52. But remember, it wants a simplified fraction. So to make life a little easier, we can just put that one into Desmos, so we're not using our brain to reduce these things. Remember, hit the fraction bar and it'll give you a reduced fraction. So the answer is actually 1 out of 13. 1 out of... Oop. Oop. There we go. Let's see if that works. There we go. So now the probability of selecting a red card. So let's go back to our standard deck here. See, we've got 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10, 11, 12, 13. We got 13 diamonds and we should have 13 hearts. Those are your red cards. Those add up to 26, right? Out of 52. But remember, it wants a simplified fraction. So for speed, let's do this one in Desmos. 26 out of the 52. And notice it didn't say anything about replacement, so it's just simply drawing it out. And see, that should be 1/2, which makes sense, right? Half of the cards are red, half of them are black, right? What did I just say? Yeah, one. There we go. Because half the deck are red, half the deck are black. Now the probability is a diamond. So let's go back over here. There's 13 diamonds, right? So it would be 13 out of 52. And believe it or not, that will reduce. I think 4 times 13 is 52. Then we turn it into our value. So what we need to put in here as a reduced fraction is a 1 over a 4. Let's check it. And then the selected card is a face card. So looking back at what we have over here, these women and gentlemen over here are your face cards. See, we got a jack, we got a queen, we got a king, we got a jack, we got a queen, and anyway, you get the idea. There's 1, 2, 3, 1, 2, 3. That's 6, 9er. 3 times 4 rows would be 12. So there's 12 face cards out of 52. And so both of those are even numbers, so we know that would also reduce. So we don't want to bog ourselves down, don't want to bog our brain down by trying to reduce a fraction, because we're being judged on time. So let's reduce it this way. So it should be 3 out of 13. There we go. Is that the problem? Alright, so here we go. This one is about summing up the table. And it's so easy, we could probably do it without any without Desmos or anything like that. Or not Desmos. We'll use Desmos because we're trying to save time here. But we're not going to use StatCrunch or anything, or Excel. It's more work. That's more work. So we're just going to work with this one. And then we'll work with Desmos to total. So what we want to do is total the men's column. Let me get rid of these right here. The men's column would be 70 plus 20, which is 90. So a 90 would go there. And then the women column would be 126 plus 36 is 162. And this column right here would be the total of this row. It also should be the total of this column. So 70, this is a good way to check and see if your two-way table is working the way you want it to do, is that both of the rows in the columns add up to the same thing. So that's your first check before you submit. And then that one was 20 plus 36. So it's 56 right there. And then we'll just double check. Let's check our rows. 90 plus 162. We got 252. Let's check the column. 196 plus 56. And we got 251. Up. I put 195. That should be a 6. And there they go. See, they both add up to 252. So that's the total sampled here. Let's check our answer. There we go. So we're 5,351. We're going to get into conditional probability, I'm going to guess. We could have copied it into Excel or whatever. It's much easier. So the probability that a person's is the, so like this is how you fold your hands, either your thumb on top or your thumb tucked in when you make a fist, I guess. Or maybe we're not making fists, we're just interlocking our, interlocking the fingers. So interlocking your left and your right, which one ends up on top. Sorry, making a fist. I didn't mean to get violent at 4 a.m., 4:30 a.m. in the morning. But anyway, so like notice that our total rights are 196. And our total out of the entire sample is 252. But remember, we want to check because it wants a simplified fraction, right? So let's get rid of these. And 196 over 152. 196 over 252. And we got that value here. Integer or simplified fraction, so that means we're going to need to do that one. 7 over 9, or it appears to be much more probable to put the right thumb on top. Alright. Now we're getting into that conditional probability. And to do that conditional probability thing, we have to calculate the probability of being right-handed given your male. So all we're going to do is take that out of the total males. So the total males was a 90, right? Well, remember, that's going to go on the bottom. The total is going to go there. But the piece, so out of the males, 70 are right thumb. And I can just look at that one and divide both of those by 10. And that would reduce down to that. Interesting thing to note, the probability of being right-thumbed is not affected by being male. And this goes into this concept of independence, which we just discussed today. Or maybe we kind of talked about it, but making it in mathy terms, this is the first time really, or today, or tonight, or yesterday, or I guess it was yesterday, class was yesterday. So notice that means they're independent, because knowing the subject, nope, that's the wrong answer. It starts getting weird here. How would we know what the events are associated? They're not associated. Associated would mean they were dependent. That would mean that these two probabilities would have to be different. Oh, and they're not. So again, the associated's wrong. It's got to be this one over here. They are independent because knowing that... Oh, here's our difference between A. This says does not change the probability. There we go. Alright. So now we're on number 20. I'm going to stop my stuff right now so I don't destroy my poorly partitioned old school computer.